Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 10-8 lesson on using sum and difference formulas. This will be a two-parter. In this one, we're going to be evaluating and simplifying trigonometric expressions using the angle, sum, and difference identities. And in part 2, we're going to be solving some trigonometric equations, some that include these identities and some simpler ones that don't. Since this is a lesson largely about angle, sum, and difference identities, we're actually going to just dive right in and get to some of those identities so we can start using them. So the following identities, and there are 6 of them, can be used when a trig function contains either a sum or a difference, an addition or subtraction of 2 different angles. So we'll start with sine. Let's say that we have sine of 2 angles. We'll call them A and B. So it turns out this is equivalent to sine of A times the cosine of B plus the sine of B times the cosine of A. Now, we're not at any point in this lesson going to derive or prove this, but I do want to show you on Desmos that this does actually give you the same values with both expressions. So let's take a look at that. So to prove my point, let's just define an A and B. We'll call A 45 and B we'll call 60. And let's see what happens if I do sine of A plus B. Great, I get some crazy decimal. That's awesome. Now let's see if I plug in the same A and B to this other half of the identity. So sine of A times cosine of B plus sine of B times cosine of A. And we get a crazy decimal that matches the first crazy decimal. This is, again, is not a rigorous proof. This is just one set of values I tried, but this at least demonstrates that this works. You know, it's proof that it works. So we're going to keep going with that, and we're going to show you the other identities, none of which we're going to prove. If you are interested in a proof, there are several videos on YouTube that you can find. They are all surprisingly long. So let's take a look at the rest of these identities. So the sine of A minus B, the good news is this is exactly the same as the first one, except that this sign in the middle is going to become a minus. So otherwise, everything is exactly the same. Sine of A cosine of B, sine of B cosine of A. Let's take a look at cosine of A plus B. So that's going to be cosine of A times cosine of B minus sine of A times sine of B. So the sign switches with cosine, whereas with sine it was the same. Now if I do cosine of A minus B, all of this stays the same, except this minus in the middle now turns into a plus. So if you know one of these, each of these pairs of identities, then you can quickly get the other one by just switching all the signs. So if you had to memorize these, that's at least one little trick you can use to cut the number you have to memorize in half. Let's take a look at tangent now. Good luck with this one. So the tan of A plus B, it's actually going to be a fraction. In the numerator, we're going to have tan of A plus tan of B. In the denominator, we're going to have 1 minus the tangent of A times the tangent of B. And then, as you might guess, tan of A minus B, all the signs switch. So we have tan of A minus tan of B and 1 plus tan of A times tan of B. So you might be wondering, what could we possibly use these identities for? And one of the big uses is finding exact value without using a calculator. Kind of like when we had to find sine, cosine, and all the other values of angles without a calculator. This is kind of in that wheelhouse. But we don't have the exact value for sine of 15. We haven't memorized that. So what we can do instead to tie into our identities is we could rewrite this angle as a sum or a difference of 2 special angles, and then use an identity. So just pause and think for a minute. How could I express 15 using some of my special angles, like 30, 45, 60? How could I put those together to get a 15? So you might have come up with the values 45 minus 30. That's what I'm going to be using in this one when I go through my solution. We're not only limited to this, there's other ways you could do it. You don't have to use 30, 45, and 60. You could use things from other quadrants as long as you could figure out the sine and cosine of those angles without a calculator. So for example, you could use 225 minus 210. It's a little bit more work and you need reference angles, but you could do it. So with all of that said, pause the video and see if you can use the identity to finish this one off. All right, so I'm going to write down the identities that I'm using each time because they're still kind of new to us, and honestly, there's a lot of moving parts to keep track of. So this is sine of a difference. So that's going to be sine of A cosine of B minus sine of B cosine of A. And maybe if you write them enough, you'll memorize them for at least a while. So this is going to be sine of 45 times cosine of 30 minus sine of 30 times cosine of 45. And we know the sine and cosine of all of these angles. At this point, we just have to evaluate all of these and simplify it as much as we can. So sine of 45, that was radical 2 over 2. Cosine of 30, that was radical 3 over 2. Sine of 30 was 1/2, so we have minus 1/2, times cosine of 45 is going to be radical 2 over 2. We can simplify this a little bit more. Let's multiply these products together. So this first one is going to be radical 6 over 4. And this next one we're going to have minus radical 2 over 4. And just as one final thing, depending on what kind of answer choices you're trying to match, we can move this into a single fraction to get radical 6 minus radical 2 all over 4. So this is one use we can use these things for. So this doesn't open a ton of new possibilities because it turns out you can really only use special angles to get different multiples of 15, like 15, 75, 105, numbers like that. So that gives you like maybe 8 new angles total that you can play around with without a calculator, but hey, it's something. For our next trick, we are given a cosine value of angle A, it's 4/5, and they're telling us A is between 0 and pi over 2, so that's quadrant 1. And we're also given the sine of some other angle, B, as this negative 15 over 17, and it's in a different quadrant, 3 pi over 2 to 2 pi. Based off of this, we're trying to figure out the cosine of angles A plus B. So the basic idea here is that at some point, if you remember what the cosine of a sum formula looks like, we're going to have to know the cosine of A, the cosine of B, and the sine of A and the sine of B. We're going to have to know all 4 of those things. They've given us 2 of those pieces already. So we're going to have to first find the other 2 pieces, and then we can put it all together using the formula. So basic strategy, we're going to use the given sine and cosine values to find the 2 missing sine and cosine values. And then we can go to town with that identity. While we're doing this, we are going to need to pay attention to the quadrants that these angles are in to figure out the sines of x and y. Because typically in both of these cases we have the r values, but we have either an x value or a y value, and we need to find the other missing one, and those can be positive or negative, so we have to be cautious about that. Also, in order to get that third missing value in each of these cases, don't forget our good friend Pythagoras. That theorem is still going to come in handy for finding x, y, or r, depending on which one you're missing. So we're going to do the first piece of this together, and then I'll have you finish it off with the other side here. So given cosine of A equals 4/5, we're going to see if we can figure out the sine of A. So in order to do this, I need to sort of break down what this 4 and this 5 means, and I'm going to start by figuring out which quadrant I'm in. 0 to pi over 2, that's 0 to 90, that's quadrant 1. And that tells me that the x and the y values that I'm going to be finding here are going to be positive values. So if cosine of A equals 4/5, and we know that cosine is x over r, that means x over r equals 4/5. And since we know that r is always positive, and we saw here that x is positive, that's telling us that x is going to be 4, positive 4, and r is going to have to be positive 5. Based off of this, we can figure out the y value. Now remember our Pythagorean theorem. X squared plus y squared equals r squared. In fact, I'm just going to write the formula right there. Might as well just cut to the chase, right? So That means if I want to find my y value, I need to do the r squared minus the x squared inside a square root. So I need the square root of 5 squared minus 4 squared. This is 25 minus 16, which is 9. Square root of 9 is 3. And I know this is a positive 3 because we already figured out y had to be positive. So now for sine, we know that sine is going to be y over r. So that means that sine of a then is going to be 3 over 5. So that gives us the third of our 4 values we need to finish this problem. Pause the video at this point. You've already got sine of b. See if you can figure out cosine of b using kind of the same reasoning, and then put it all together and let's see if we can get the answer. All right, so we are in which quadrant here for the b angle? Well, this is quadrant 4. This is 270 to 360. In quadrant 4, x is still positive, but y is negative because we are below the x-axis. So we know that sine of b in general is going to be y over r. And we just established that y is negative. So since this is negative, that means that the negative has to go with the 15. That's got to be the y value. So we have a negative 15, and r is always positive, so that's going to be 17. Now we're going to use our Pythagorean theorem to get the x value. We can write that the x value equals the square root of 17 squared minus 15 squared. And I know this is going to come out to a positive x value, again, because I already figured out in quadrant 4, x's are positive. So you might need to brush up on your perfect squares, because this is all supposed to be done without a calculator. But this is 289 minus 225, and that comes out to 64. The square root of 64 is 8. Or you might remember from back in geometry the 8, 15, 17 right triangle. That would also be helpful. This here was a 3, 4, 5 triangle, so here's a place where those might be pretty useful. In any case, we know that cosine of b is going to be x over r, so that's going to be 8 over 17. Putting it all together now, we know that the cosine of a sum in general is cosine of a times cosine of b minus sine of a sine of b. So fitting all these things in here, cosine of a they gave us, that was 4/5. Cosine of b we found down here, that was 8/17. Sine of a, we had to find that ourselves, that was 3/5. So we're subtracting that, times the sine of b, which they gave us, was negative 15 over 17. All right, let's see if we can simplify this a bit. So 4 times 8 is 32. 5 times 17 is 85. So we have 32 over 85. Minus minus gives us a plus. This will be 45 over 85. Thankfully, it's the same denominator, so we can just add the numerators now, and that ends up being 77 over 85, which I believe cannot be reduced. For this next problem, they're just asking us to simplify this expression, probably with one of those lovely identities we've got. So that's really all you have to do on this one. Just use the identity and see what happens. Pause the video, give it a shot. All right, so we have a tan of a difference. That's going to be tan of a minus tan of b over 1 plus tan of a tan of b. So plug in all that in. We've got tan of x minus tan of 2 pi over 1 plus tan of x times tan of 2 pi. Let's go ahead and simplify these tans that have constants in them. Now the tan of 2 pi, that's basically the slope at 360 degrees. That's a horizontal flat line, so that's a slope of 0. So this is tan of x minus 0 up top. And then since tan of 2 pi is 0, that's going to zero out this whole tan of x kind of expression here. So what we end up with then is just tan of x in the numerator, and this is 1 plus basically 0, so just 1. Tan of x over 1 is just going to come out to tan of x. So we're going to do another one of those simplify with an identity problems. This time we have tan of a sum, and you might be thinking, oh, I know the tan of a sum, at least I've got the formula written down. Let me just plug all this in and see what happens. There is one little problem though, and this is the reason I titled this How Not to Get Burned by Tan. Tan of pi over 2, which you're going to have to evaluate if you actually plug this in the tan sum formula, tan of pi over 2 is undefined. Tan, remember, is the slope, and this is asking for the slope at 90 degrees, which is a perfectly vertical line. We know vertical lines are undefined for their slope. So since tan of pi over 2 is undefined, that means using the tan of a plus b identity is not actually going to work. It's going to give you some kind of error. So there is a little bit of a workaround for this. There is another way of expressing this. Tangent, we know, is also expressible using sine and cosine. So that's going to be our trick here, is we're going to rewrite this with sine and cosine. We can split this up into sine of x plus pi over 2 divided by cosine of x plus pi over 2. And the beauty to doing this is that, first off, we know formulas for sine and cosine of a plus b. We've got those formulas. The other thing is those formulas use exclusively the functions sine and cosine, which are all defined at pi over 2. So we're not going to run into that undefined issue. So with that said, pause the video and see if you can take this one the rest of the way. All right, so I'm going to rewrite this with the full formulas. So we're going to have sine of a cosine of b plus sine of b cosine of a. That's what the whole numerator of this thing is going to look like. And in the denominator, again, we'll have cosine of a cosine of b minus sine of a sine of b. Now it's time to plug in our angles. So we've got sine of x times cosine of pi over 2 plus sine of pi over 2 cosine of x divided by, down here we have cosine of x cosine of pi over 2 and minus sine of x sine of pi over 2. All right, let's go through and simplify these a little bit more. Anything with a constant we can simplify. So cosine of pi over 2, that's the x value at 90 degrees. That's going to be 0. And sine of pi over 2, that's the y value at 90, so that's going to be 1. So we have 1 times cosine there. And then down here, again, cosine of pi over 2 is 0. And sine of pi over 2 is 1. Let's keep going. So we've got sine of x times 0, that's just 0. 1 times cosine of x is just cosine of x, so that whole numerator is just cosine of x. And down here, let's see, anything times 0 is 0, and this is going to be a minus sine of x. And then if we want, we can simplify that to be negative cotan of x. So this is the end of part 1 of our lesson on using sum and difference formulas. At this point, you can pause the video and try out some of these simplifying and evaluating sort of problems with these different formulas. And come back, we're going to tackle trigonometric equations in the next part. Welcome back. You are joining us for part 2 of our lesson on sum and difference identities. In this one, we're actually focusing exclusively on solving trigonometric equations, some of which will have those identities that we learned about in the first part. Now, we're going to start by defining what a trigonometric equation is, because the techniques we're using here to solve them don't apply to other types of equations necessarily. So by trig equation, I don't mean an equation that has a trig function in it. That's a precondition, but it's not enough. We mean specifically for a trig equation, one that has a variable inside a trig function. For example, this equation down here. This theta here is inside the trig function, and that means that I can't just like divide by something to solve for it. I have to do some inverse trigonometric reasoning to get this variable out of the function. So given that, generally on these problems, that means that we are usually solving for some kind of angle or angles, and specifically we're solving for angles that have a certain x or y value or a certain slope value. And let's just review which trig functions go with which of those, because that'll be very important for what we're doing here. So remember that cosine of theta is the x value of theta. So if I have cosine of theta equals some number, like 2 for example, or 1, 2 actually wouldn't work, but let's say it equals 1, I'd basically be asking, at what angle do I have an x value of 1? So if you know what these trig functions mean in terms of x, y, and slope, you can use that to ask questions that kind of help you solve the problem. We know that sine of theta is the y value. And if I have tan of theta, then I'm being given a slope value, which I'm going to call an m value, that I have to kind of reverse reason and figure out what angle that could be. So you actually have solved trig equations before. When you were doing SOHCAHTOA right triangle trig problems, you had to set up something with sine, cosine, or tangent, and then you had to set it equal to some ratio. And then if you were solving for an angle, you had to use your inverse trig functions on your calculator. There's two little wrinkles that we're going to encounter in today's lesson. One of them is that you're not going to get to use a calculator. Everything we're going to be doing is going to be without a calculator, and we'll talk about how to work around that. The other big game changer here, is that we're no longer just solving for a missing angle in a right triangle. If you're just looking for a missing right triangle angle, you're limited to values between 0 and 90, because a triangle only has 180 degrees, and you've used up 90 of them with the right angle. Here, we have the interval from 0 to 2 pi. That's the whole circle. The difficulty with this is, in just the first quadrant of the circle, there was only one angle that gave you each x, y, and slope value. On the interval from 0 to 2 pi, the whole circle, we can usually find two answers, two angles that give us the same x, y, or m value. So we're going to have to be aware of that, and we're generally going to be finding more than one answer on these. So with all of that said, let's get started on doing this one. So we're going to start this one together. A good first step to take on all of these problems is to isolate the trig function. We basically want to get one of these three cases up here where we have sine, cosine, or tangent of some angle, and that's it, equals some number. If we can get to that situation, well, we're halfway there. So in this case, to isolate cosine of theta, what do we have to do? Oh, we just have to divide both sides by 4. Okay, well, 0 divided by 4 is 0. So the isolated version of this is just cosine of theta equals 0. Great. Now what? At this point, we're going to actually draw the angles that have the x, y, or slope value from this equation. So I'm going to draw a little unit circle here. And I basically want to draw the angles where we have, let's see, this is cosine, so angles that have an x value of this number, 0. So where on the unit circle do I have 0 for x? Well, x is 0 on the y-axis here. So that's going to be up here. That's one angle that would have an x value of 0, and also down here, so two different angles. If what you've just drawn, if those angles are quadrantal angles like these ones, you can just read them off the circle and just express your answer in radians, because that's what this means here. If they're not quadrantal, stay tuned and we'll worry about that in the next example. So pause the video and see if you can finish this one and see which angles solve this equation. Alright, so this wasn't too far-fetched or difficult. We just had to convert these numbers to radians. 90 degrees is pi over 2 radians, and 270, just multiplying by pi over 180 and reducing, that's going to be 3 pi over 2. So for this problem, we've got another example where we're trying to solve between 0 and 2 pi for this angle here. Pause the video and see if you can at least get to the point where you're graphing these on the unit circle. Alright, so let's see how far we got. First, we want to isolate that trig function. So add 1 over to the other side, and then we can divide by 2 to get sine of theta by itself. So we have sine of theta equals 1/2. So we're asking essentially, since this is sine, where does the y value of the angle equal 1/2? So let's graph our unit circle here, and we're asking where y equals 1/2. So on the y-axis, 1/2 is roughly here. So on the circle, we've got a spot right about here and another one over here. And this is a little bit of an issue because these are not quadrantal angles. So I don't really know what this angle is. I mean, I can make a guess at it, but I don't really know for sure. So here's a process you can follow if you don't get a quadrantal angle when you graph these out. First off, we didn't do this for nothing. Does still give us some good information. We're going to start by at least writing down the quadrants if these angles are not quadrantal. Write down the quadrants, and we'll at least know which quadrants our answers are going to be in when we finally are able to calculate them. So in this case, we're in quadrants 1 and 2. And really the only way to know that out, again, was by drawing this out and graphing it out here, or you might be able to visualize it in your head. So how can we figure out exactly which angle it is? So the next thing we're going to do is figure out the reference angle. So we'll find our reference angle, which I'm going to call theta prime, just kind of in keeping with how we've been noting it in this chapter. And I can find the reference angle by doing looking up a positive x, y, or m value in my special angle value table. So here's that table that we saw a few chapters ago. We had the sine and the cosine values of 30, 45, and 60. We had radical 3 over 2, radical 2 over 2, 1/2, and kind of going the other direction for sine. And then it didn't make the first version of this table, but I'm throwing it in there because it'll be very helpful. Tan of 45 we saw was actually 1. So to figure out the reference angle for whatever our answers are going to be, what we're going to do is, if this number right here that the trig function equals is not already positive, which in this case it is, we're going to pretend it's positive. And we're going to look up that value with the trig function in this table. Or you might have all this memorized and be able to just kind of look it up in your head. So I'm asking, okay, at what angle does sine equal 1/2? Well, sine 1/2, that goes with an angle of 30 degrees. So 30 degrees is our reference angle. Now, what does that actually do for us? The reference angle, remember, tells us how far we are away from the x-axis at whatever angle we're actually at. So the reference angle visually is telling us this distance right here, and it's also telling us this distance right here. Well, if you know how far this distance is angle-wise, and you've already got an angle that you're starting at, and same kind of thing over here, you can use this to figure out what these angles are just by using this reference angle. So in general, we're going to use our reference angle to get these quadrant answers, which are actually our final answers once we express them in radians. And specifically, we're going to be adding or subtracting your reference angle to the closest x-axis angle. That'll get you to the angle that you need to get to. So with that in mind, pause the video and see if you can finish this one off and figure out our quadrant 1 answer and our quadrant 2 answer. All right, so for our quadrant 1 answer, the closest x-axis angle is 0 degrees. And we're just going 30 in the positive angle direction, so that brings us to 30 degrees. And in general, if you're looking for a quadrant 1 answer, your reference angle will be that quadrant answer because the reference angle is already between 0 and 90 degrees. All right, now over here in quadrant 2, we're closest to the 180 angle, and we have to go 30 degrees backwards to get into quadrant 2. So that would be 180 minus 30, which would give us 150 degrees. And then as a last step, converting these into radians, 30 over 180, that's going to be pi over 6 radians. And then 150 over 180 reduces to 5 over 6, so 5 pi over 6 for that one. Here's another example for us to try out. When you isolate the trig function on this one, you might need to simplify the radical that you see in order to match with something in that table. So with that little hint in mind, pause the video and give this one a shot. All right, so to isolate this trig function, we divide by negative radical 2. So we've got negative 1 over radical 2. And to simplify that, I'll multiply by radical 2 over radical 2. That gives me negative radical 2 over 2. So that actually matches something in my table. But first, let me figure out what quadrants I'm in. So if I have cosine equals this, I'm basically asking where does x equal negative radical 2 over 2. I'm not sure exactly what radical 2 over is. I think it's like 0.7 or something, but that doesn't really matter as long as it's between 0 and 1. I do know that I've got an x value somewhere over here that matches this, and another one down here in this quadrant. So that's going to be quadrants 2 and 3. And again, I don't need to know exactly where this thing is on the unit circle. If it's not a quadrantal angle, all I really am trying to figure out at this point in the game is which quadrant I'm in. What I am going to need now in order to figure out the exact angle is that reference angle. So I'm going to pretend that this is a positive radical 2 over 2. And cosine of what angle in that table gives us positive radical 2 over 2? Well, cosine and also actually sine of 45 degrees gives us this. So again, you might already be able to have that memorized and recall it, or if you got that table in front of you, that's helpful. So 45 is our reference angle. So in order to get our quadrant answers now, let's do quadrant 2 first. So we're starting at 180 and we're going 45 degrees backwards to this angle. So 180 minus 45 is giving us 135. And then, let's see here. Let me just take a step back and show how I got that. So again, that was 180 minus 45, giving us 135 degrees. Now for quadrant 3, we're starting at 180 again, but this time we're going forwards 45 degrees. So 180 plus 45, and that's giving us 225. Converting these to radians, 135 over 180, that'll reduce to 3 pi over 4 radians. And 225 over 180 reduces to 5 pi over 4 if you reduce by 45 degrees. This next example is going to be a lot of fun. We have tan of theta minus pi over 4 equals 0. So on this one, in problems like this in general, where you have a sum or a difference of angles, it's a good idea to simplify those angle sums and differences first before you do any of those other techniques we talked about, because everything we talked about assumes that you have just a theta inside the function. This other stuff kind of muddies the waters. So with that in mind, see if you can use an identity and turn this into something that's a little bit more resembling what we had in the last few problems. Pause the video and see how far you can get with this one. Alright, since I have a tan of a difference, I'm going to use my tan of a minus b formula. So again, that was tan of a minus tan of b over 1 plus tan of a times tan of b. So in this case, we've got tan of theta minus tan of pi over 4 over 1 plus tan of theta tan of pi over 4. So now simplifying this a little bit here, we've got tan of theta minus, this is tan of 45 basically, which we know that special value, that's 1. So minus 1 equals, well, now we could simplify all this stuff down here, but at some point we're going to have to multiply this to the other side to get it out of the denominator. And once we do that, well, all this stuff times 0 is just going to give us 0. So that actually works out really nicely. Now to isolate the trig function, all we have to do is just add 1. And at this point, let me go ahead and do my little unit circle dance because I've got an isolated trig function. So since this is tan, this is the slope of the angle, I'm asking where does m, the slope, equal 1? Well, there's two places that happens. We have a slope of 1 somewhere here in quadrant 1. If we drew an angle in here somewhere, it would be at least a positive slope, so somewhere in here. And then back here in quadrant 3 as well, this would also give us an angle that's going up and to the right as we move to the right there. So now, what are these angles exactly? Well, let's get the reference angle. Doing a reverse lookup in our table, we know that tan of 45 equals 1. So that's our reference angle, and we're going to use that to figure out quadrant 1 answer and quadrant 3 answer here. So reference angle of 45 degrees. Quadrant 1, that actually is the answer. It's between 0 and 90, so we've got 45 degrees right off the bat. For quadrant 3, again, we're starting at 180 and adding the reference angle. So add 45, and that's 225. Looks very familiar. So converting these to radians, 45 over 180, that would be pi over 4 radians, and we actually kind of saw that up here. And 225, we did this on the last problem. That is still 5 pi over 4. All right, gather all your strength and steel your courage here for the final boss battle. This one has not one, but two sum, difference, identity kind of things going on in it. And they're different identities as well. So this is kind of the worst possible case here. How can we deal with a situation like this? Well, just like before, simplifying those angle sums and differences beforehand is a really good idea. I think this is just one where you have to play it out and see where it goes using your identities. Pause the video and give this one a shot. All right, so we have two different identities, but they're not that different, right? They're both cosine identities. So I'm just going to rewrite my cosine identity a little fancier than I used to. So cosine of A plus or minus B, we know that's going to be cosine of A and cosine of B. We know that the sign between these things is going to be the reverse of what we started with. So I'm going to write minus plus instead of plus minus. And then we have sine of A and sine of B. So I've got cosine of theta times cosine of pi over 6. And then we're going to be, let's see, since we're doing a plus in the beginning, we're going to be subtracting. So this is going to be minus sine of theta times sine of pi over 6. And then I've got all of this other identity over here. I'm going to put everything from this one in a parentheses. So I'm going to have a minus parentheses. And I'm going to have cosine of theta times cosine of pi over 6. And since this is negative for this theta pi over 6 pair, this will be a plus in here. So plus sine of theta sine of pi over 6. All of that equals that little 1 at the end. Now this looks like an absolute mess. But there is some good news. So if we were to distribute this negative, we would have a negative cosine of theta cosine of pi over 6. Well, over here we have a positive cosine of theta cosine of pi over 6. So this cosine and this cosine are actually going to completely cancel out, which is awesome. We also have this minus sine theta sine pi over 6. And in here, this is going to be another minus sine theta sine pi over 6 once I distribute this negative. So if I have two of those, I can write negative 2 sine of theta sine of pi over 6 equals 1. So that is a lot nicer than what we started with, but it gets better. Sine of pi over 6, we can actually simplify that. That's just the sine of 30 degrees, which you might remember is 1/2. So we've got a 1/2 right there. This negative 2 and the 1/2, if I multiply those, that's just negative 1 times the sine of theta. And we can very quickly isolate sine of theta by dividing both sides by negative 1. So we have sine of theta equals negative 1. We've got our trig function isolated. It's time to graph this on the unit circle and see what we're looking at. So on the unit circle, I'm asking where does y, because again this is sine, where does y equal negative 1? So going down to negative 1 on the y-axis, that's down here at the bottom of the circle, there's only one spot right here where that is true. And this is kind of a rarity. Usually we get two different spots. This time around it was just the one. And that spot is 270 degrees, which I can also write in radians as 3 pi over 2. And with this problem, we are concluding our lesson here. We've learned about sum and difference identities. We've learned about solving trigonometric equations. And we've learned that, hey, we can put two things together and still come out on top. So until next time, this is Mr. Sutton signing off.